Part B of Module 4, Basics of RISC Architecture. In this part, we will learn a very important architecture in CPU microprocessor, RISC architecture. Part B.1, CISC and RISC architectures. First, let's look at the CISC architecture. What's the meaning? Meaning of this CISC. Complex Instruction Set Computer. CISC. All right. So let's look at the properties of this. Two major architectures. The first one, CISC architecture, all instruction can execute several low-level operations. What are low-level operations? Here you can see some example. Load data from memory. After we learn cache memory part, cache memory, our module 3, we need to load data from memory. So here, there is some special operation in CPU, so we need to load the data from memory. So that's a low-level operation. And arithmetic operations. So what is arithmetic? Addition, multiplication, division, subtraction, things like that. Arithmetic operation, a memory store data, so write it back to memory. So that kind of thing, low-level operations. It can also do multi-step operations, multi-steps. One operation that is relatively complex. So for this reason, why we use complex, multi-step to make this operation more complex, comparing with later simpler type, simpler operations. All right. So multi-step operations. So this operation needs to do several important tasks. So multi-step operations. And it supports multiple addressing modes. Addressing modes. How to get data, in what specific way to get data from memory. You need to use some special addressing modes. So later, we will discuss a long list of addressing modes. Here, you only need to know some special way to get data from main memory. Addressing modes. Multiple, Next one, the term was retroactively coined. The term, what term? CISC term. This term was not created when this architecture was developed. When this architecture was developed, there is no name for it. Because people only knew that architecture. That's the only one. Okay? So they didn't provide any name for it. But later, after they created another new architecture, RISC architecture, so we will talk about in next half slide, RISC architecture, then people felt they should provide a different name for the first architecture. So then the CISC name was, coined. So that's why retroactively coined. In contrast to RISC, what's that? Reduced Instruction Set Computer. the main difference, reduced versus complex. Reduced, make it simpler, yeah, simplify it, reduced, yeah, versus complex, not reduced, complex. So why complex? Multi-step operations. Yeah. Later, we will explain why complex versus reduced, yeah, because a lot of discussion on that. Okay? Yeah. All right, so later we will look at that question. Yeah. All right. The instruction sets directly support instruction sets of the CISC, right? CISC type instruction sets directly support high-level programming constructs, such as procedure call, loop control, and complex addressing modes due to weak software support. All right, so the last sentence is important. The last sentence probably gives you some reason why complex versus reduced here. Why is that? The reason is very simple. Weak software support. Because at that time, the software support was very weak. What kind of software support? Compiler. Yeah. Because at that time, even there was no compiler. There was no compiler. Yeah. So very early time. So no compiler was available to, handle the complexity. Then, in the instruction set level, the designers, they had to create some special instructions to handle relatively complex operations. Later, at the RISC time, there was compiler, compiler technology, software support was available. Then, no complex operations are needed anymore. So then reduced instruction set. Better choice. Yeah. All right, yeah, so that's the CISC architecture, the property. Next, let's look at the RISC architecture. Meaning, yeah, we saw it, reduced instruction set computer. Properties. First, it has a small set of simple and general instructions, rather than a large set of complex specialized instructions. So when you compare with the CISC instruction set, you can see small set. So the number of different instructions, the number of different operations, instructions, smaller, much smaller, and also simpler. In each instruction, you do not need to do multi-step operation. You only need to do single-step operation. Because for the complex task, you rely on compiler to, organize different operations, putting different operations together. All right, split, putting together, compiler will do that work. But in the instruction level, we just make it as simple as possible. The result is also obvious. The result, we can get faster performance. Faster performance. So later, we will see why we will get faster performance. So in this special simplification, reduction, actually, we will get a faster performance using RISC architecture than using CISC architecture. All right. Memory, yeah, another property. How to, in order to make it perform faster, another special way to do it. Yeah. Memory is only accessed through specific instructions. So what specific instructions? Load, store, right? Yeah. So we just talk about, yeah, load instruction, we need to access memory, right? Store instruction, we need to access memory, right? Other than these two types, other instructions cannot access memory. Yeah. In this way. So you designers, yeah, now you designers, they enforce this rule. Yeah. Memory is only accessed through specific instructions rather than as part of most instructions. Because another way, most instructions can access memory if they need data from memory. So that's another way. So later we will compare it. Yeah. So in the later part of this part B, so we will see that. Okay, so other instructions, they can also access data from main memory. Yeah. So you can compare which way is faster. Yeah, we will see that. Yeah. This way will be faster if we look at the overall performance of one program. All right. Next, simplified memory addressing modes. So this way can also improve the performance. Yeah. Simplify memory addressing modes. Why simplify can make better overall performance? Yeah. Here, I just explain a little bit. Later, we will see that more. Yeah. Because in order to represent all the number of addressing modes, you need to use certain number of bits in your instruction, right? Instruction is composed of bits, certain number of bits. Yeah. So the now encoding the number of addressing modes, you need to use certain number of bits. The more addressing modes you need, the more bits you need in your instruction, right? The more bits you need in your instruction. Okay? Yeah. So in that way, you use more bits. So then your instruction could be longer, right? Yeah. Could be longer. Yeah. So then you need to use more bits. Okay? Yeah. So if you do the same thing, you use more bits. So then your code is, less efficient. Yeah. So that's the understanding. Yeah. So later we will understand that part more. Yeah. All right, next, we have a few more properties for RISC architecture. Yeah. Another one, it's called fixed length instructions, commonly 32 bits, and a simple encoding. Yeah, fixed length. Yeah. Later you will see versus variable length. Variable length means some of instructions longer, some instructions shorter. So variable length. Fixed length. Then when you do decoding, yeah, compiler, you rely on compiler to do decoding, right? Encoding, decoding. Compiler can do faster, right? Fixed length. You can make good prediction. Yeah. So I just try to extract information from this instruction, here and there, much easier, right? The variable length, much harder, okay? Sometimes you need to look at more bytes. Sometimes you need to look at, fewer bytes. So the increased complexity will reduce the overall performance. Yeah, so that's another way, this RISC architecture is faster. Yeah. Gaining performance through the use of pipelining. Yeah, this technique is very important. Yeah. Later, we will spend a lot of time to study this pipelining, using a pipelining way to do instruction level parallelism. Okay, yeah. Pipelining, we do instruction level parallelism. All right, parallelism. Okay. Yeah. That's a big topic. Yeah. All right. Using more instruction. Yeah. So here, right? So in the pipelining, yeah, I just repeated. In the pipelining, we will explore more instruction level parallelism. The method is very smart. The method is very smart. Yeah. So we will get there. Yeah. All right. Next one, another very important architecture, 80x86 architecture. Okay. So that's the Intel. Yeah. So you know, Intel use this architecture in PC. So we're familiar with that. PC, Intel. Yeah. So this architecture, closely related to these two architectures, both CISC and RISC, a combined way using CISC and RISC. Yeah. Some people got a misconcept. Some people misunderstood or misunderstand in this way. They feel Intel, they just use the CISC architecture. That's false. Yeah. Actually, their architecture, most part RISC, then smaller part CISC a little bit. Smaller part CISC. The major part RISC. Yeah. So let's look at the properties. Yeah. Combine features from CISC and RISC. Why? There is some reason. There is some very good reason Intel used this special architecture, and it is very successful in the market. Yeah. All right. So internally and externally. Internally, not related to the users, just internal, CPU side. Yeah. Internally, RISC instruction set for performance. Yeah. So for users, for outside people, we do not need to deal with that part directly. Okay, so internally, so in order to get faster performance, so they use the RISC architecture. Yeah. But externally, different. Externally, so they use their special architecture instruction set. Yeah. All right. Binary compatibility with PC software for programmers. You can see why they do that, because they want to make the programmer's life easier. They want to provide a convenient interface for programmers. Okay, yeah. So for that reason, so they make that interface part sometimes longer instructions, sometimes shorter, sometimes more complex, sometimes simpler, make adaptive, make their external part of the instruction set, variable length, right? Longer, shorter, for the programmers. Yeah. All right. But external way, internal way, different, so they need to do translation. Translate the external way to internal way. Yeah. All right. Use hardware to translate from 80x86 instructions to RISC-like instructions. internally RISC-like. Yeah. So very close to the RISC, but slightly different. So that's why they call it RISC-like. So that's why I said major part RISC, only, smaller part, minor part, interface part, CISC. Yeah. 80x86. Yeah. Closer to the CISC, yeah, but still slightly different from CISC, yeah, because that's their own way. Yeah. This architecture their own way, Intel their way. Yeah. All right. So with this kind of special architecture, the market shares, let's look at these several major important sections in the market. Yeah. Personal computer and the laptop section, yeah, dominant by this x86, dominant by this architecture, Intel's architecture. AMD also uses this architecture. Okay, AMD also uses this architecture created by Intel. Yeah. All right. Yeah. But definitely, so they modify, use their own way. So, their proprietary property. So they, modify this architecture. But the, foundation, x86 architecture. Yeah. Smartphones, tablets dominated by ARM architecture. ARM, okay, yeah. So for the cell phone, tablet, some relatively smaller computing devices, yeah, very successful. This ARM architecture, very successful. Yeah. Yeah. Later we will see ARM a little bit, but ARM is a special type of RISC. Yeah. ARM belong to RISC architecture, special type of RISC architecture. Yeah. ARM. Yeah. High-end servers also dominated by this architecture, x86 architecture. All right, yeah. But recently I just got a news, NVIDIA, they use ARM to do the server-side processor. They design chips used at the server side, but they use the ARM architecture. Yeah. ARM architecture so usually consume less energy, power and energy. Yeah. And but computing power is weaker. So if we compare with x86 architecture uses more energy, power, energy, yeah, but computing power also larger, yeah. But the ARM, yeah, because in the smartphone we want to save more energy, right? So we want to save more power, energy, yeah. So we do not expect computing power very fast comparing with PC, right? We do not expect the PC computing power, right? So nobody expect that. Yeah, just reasonably fast. So ARM can deliver that. Yeah, but the server, so we really want to have big computing power, right? Server very fast. Yeah, people are willing to pay a little more power bill to get faster performance. Yeah. But why recent trend, NVIDIA, so they use this ARM architecture to do the server-side computing. Yeah. The reason also reasonable, yeah, because first they can improve the performance. The performance although not as fast as x86 processors, but reasonably fast. Another good thing, consume much less power and energy, save a lot of electricity bill. That's also attractive, right? For some companies, it's pretty attractive. Yeah. So that's the reason there is a market need. Yeah. Some companies, they like that way. Yeah. All right, so we finish our